So we finish our session with the talk by Lorenzo Liverani, who is a postdoctoral researcher here at the chair. Please. Thanks.
Okay, thank you. And so today I'm going to discuss about, I will bring the topic back to more like abstract mathematics, and but let's say, I was inspired by the talk of yesterday by Professor Charton on the Lyapunov functionals, right? On discovering Lyapunov functional, and I thought, well, I recently published a paper where we introduced an algorithm to discover Lyapunov functionals. So, and I understand this will not be machine learning, but I hope you will find it interesting anyway. And the paper in question is the one you see here. So, as the title says, it is concerned with the asymptotic dynamics of hyperbolic systems with non-symmetric relaxation. This was a joint work with Timothée Krembarat, which was here at the chair until last year, Lingyun Shou, and obviously Professor Zozua. And so this kind of topic here gets very, let's say, technical very quickly. So I tried to keep it as simple as I could, and I also didn't want to bore you with technical details. So what I did is that I structured this talk like a video game. So you will help me solve levels of this video game, and hopefully at the end of the talk you will understand more or less how our algorithm works. And of course, you will have to indulge me. I will not be as precise as I should be probably, but I just want to give you the main idea, and then of course we can discuss details together later. So the video game is called, Does the Energy of the System of Hyperbolic Partial Differential Equations Decay? Which is not a good title, but I'm working on it. However, it has all the ingredients for what we want to do. Okay, so we have a system of hyperbolic partial differential equations. To this system is associated an energy, and we want to know if, as time goes to infinity, this energy will go to zero. Okay, so in any video game, the first level is always a tutorial. So let's start with a very simple equation. This is not even a system, okay? This is the easiest hyperbolic equation you can think of. And let's see what are the rules of the game, right? So the equation we are given is partial derivative in time plus partial derivative in space. This is the general structure for an hyperbolic equation, plus u equal to 0. Here the space variable, and this is very important, in this work will always belong to R, so to the unbounded domain. And the energy of this system is always the L2 norm of the solution. So whenever you see the symbol of a norm in this talk, this is the L2 norm. Okay, it's not specified, but it's always the L2 norm. All right, so the question is always the same. Does the energy of this system decay as time goes to infinity? What do you say? I don't know. Unfortunately, Enrique is not here. When I presented this the first time, he was the first to raise his hand, because obviously for him it's easy. Who says yes? Raise your hands. Okay, who says no? Okay, well, you are right, Luis. So the energy here indeed decays. Okay, how do we show this? Well, there are several ways. And in fact, in this case, you could even write the solution directly if you knew the initial data. But what I like is precisely to find a Lyapunov functional, okay? And there are several ways to find Lyapunov functionals. I don't use transformers. What I use is a method called the perturbed energy method. So the idea is, or the technique of multipliers. So the idea is you take the equation, you multiply in L2 by a certain functions of the variables at play. So in this case, the function is very easy. You just multiply by u in L2. And by doing this, you obtain the sum of three terms. The first one is UTU, which is simply the derivative of the energy in time. The second one is actually equal to 0, and here it's very important that x belongs to the unbounded domain, because we don't have boundary conditions. And finally, the third one is simply the L2 norm of u. But the L2 norm of u is the energy itself. So we have obtained that the derivative in time of the energy plus twice the energy is equal to 0. And by the Gromval inequality, in this case even an identity, you can show that the energy decays exponentially. Okay, so this completes the first level. All right, so this is the general idea. Okay, so let's move to a more complicated level. And let's start to look at systems of equations. Okay, so this is a very simple system of hyperbolic equations. As you can see, the first equation in U1 is coupled to the second equation by this term here. Okay, so in the first equation, you find u2x, so the derivative in x, and in the second equation you find u1x, okay? The energy of the system, again, is the sum of the L2 norm of the two variables, and we want to know if this energy decays. So I will not ask every time, what do you think about the system? I will tell you what to do in this case. So the first step is always inspired by what we saw before, to multiply each equation by its own variable. This will give us the derivative in time of the energy. And we can do it here too, okay? So you multiply first equation by u1, second equation by u2. What you obtain is that the derivative in time of the energy plus the norm squared of u1 is equal to 0. This is very similar to what we obtained before, but now there is a crucial difference, okay? Which is that the energy also contains the norm of u2. So this is not enough to do what we do earlier, okay? So we need to recover also the norm of u2. And how do we do this? Well, if you're used to this kind of idea of the multiplier, the technique is generally the same, okay? So you look at the energy that you recover, u1, you go to the equation for u1, and you check what are the variables connected to u1, in this case u2. So you take the first equation, and you want to multiply by a certain function of u2, okay, so that you recover the norm that you're missing. Okay, now in this case, you cannot multiply by u2, because otherwise you would obtain the scalar product u2x u2, which is equal to 0, as we said. So what we do is we multiply the first equation by u2x. What happens? Well, what happens is a lot of computations which you don't have to read. The important part is that at the end of these computations, after you use the Cauchy-Schwarz inequality, you obtain that the derivative of a certain scalar product minus a certain term containing the norm you recovered at the beginning, plus the norm you wanted to recover, is smaller than or equal to 0. Okay, so in the end, what we found were these two inequalities here. So to obtain the energy, so we have the derivative of a certain, of two terms, okay, plus certain terms, which we would like to contain the energy of our system. Unfortunately, you see, there's a problem here, because the energy would be u1 plus u2, not u1 plus u2x, okay? So how do you get rid of this derivative in u2? Well, here's the only technical part of this talk, which I will skim very quickly, okay? The main idea is to pass to Fourier coordinates, okay? So you transform everything using the Fourier transform, and this gives you, and here it is also very important that your space variable is in the whole unbounded domain, okay? But you transform everything using the Fourier transform, and then you notice that the derivative in space now becomes a weight, okay? Which is a weight in the frequency psi, okay? So now you can actually combine these two inequalities, okay, by simply multiplying the second one by a certain small constant epsilon, okay? So for instance, if psi is bounded, okay, then by multiplying by epsilon small enough and summing up the two inequalities, you find exactly that the derivative of a certain functional, which is your Lyapunov functional, plus the energy, is smaller than or equal to 0. And this, by Gromwall inequalities, which I don't want to bore you, will yield the decay of the energy. Okay, so just to summarize, okay, this just says what I just mentioned. Okay, you can define a certain Lyapunov functional L, where, so the first part is just the norm of your solution, just the energy, and the second part is this extra scalar product that you find here, weighted accordingly. Okay, the weight will depend on the frequency that you choose, okay? Basically, again, if the frequency is bounded, no problems. If the frequency is unbounded, the weight has to account for the unboundedness of the frequency, okay? So if the frequency is very large, you want a weight that is 1 divided by the frequency, okay? And then you do some computations, you find that the derivative in time of this functional plus a constant times the functional itself is smaller than or equal to 0. So this shows that you have exponential decay in high frequency and polynomial in low frequency, and this completes the level. Now you might say, okay, well, this was a 2x2 system, okay, very easy. How does this scale to more complicated systems? Well, thankfully, Professor Zouazoua and his collaborator at the time, Karim Bochard, were very good at playing video games, And so they discovered that there is a structure in how we do this kind of computations, okay, in how we do these multiplications for, to obtain the decay. Okay, so they said, instead of looking at the system as a system of two equations, let's just write it as a single equation in vector form. Okay, so U will be the vector U1, Un, A will be a symmetric matrix, and B an hypocoercive symmetric matrix, meaning that it's simply a symmetric matrix that satisfies an equality of this kind. So basically, it is coercive only on some components of your vector big U, okay, that we will call X here. So suppose that your system can be written like this, and just to make an example, in the system we just saw, this decomposition looks like this, right? So you see that A is a symmetric matrix, B is also symmetric, and is hypocoercive in the sense that you see here, right? So BU times U is just equal to U squared, okay, which in this case is our kappa times X squared, okay? So suppose you're in this context here, then Bouchard and Zozua in 2011 showed that if A and B satisfy the Kalman-Rank condition, which is a very famous condition in control theory, then you have the kind of decay that we just saw. Okay, so exponential in high frequencies and polynomial in low frequencies, all right? The Kalman-Rank condition, for those of you who don't know, is this condition here. It's an algebraic condition that tells you that the rank of this very big matrix that you build by multiplying together B and A has to be equal to N, okay? Now, it's very interesting to see how does the Kalman-Rank condition appears from the computation. So suppose that you have your system written in vector form, okay? And let's try to do, again, the computation that we saw earlier just in vector form, okay? So at the beginning, what we did was to multiply by U1 and U2. This means that we take this equation and we multiply by big U in L2. So what happens is that you get, again, three terms. The first one is the derivative of the energy. The second one you can show is equal to 0. This follows because A is symmetric. And the third one is precisely the hypocoercive term, okay, is BUU. So this gives you that the derivative of the energy plus kx squared is smaller or equal to 0. Obviously, in the system before, this was telling us that the derivative of the energy plus U1 was equal to 0, okay? Now what do we do? Well, consider now the scalar product, which is BU, BAUX. This seems very, very random at this point, okay? So I understand if it seems like you're not following, but I promise that it will make sense in a minute. So consider this scalar product. You do your computation, you take the time derivative, okay? And again, you don't have to look at the computation, but just look at this last line here, okay? So what you find is that after you do all of your computations, you are recovering the norm BAUX squared. Again, at this point, you will say, why do I care? Okay, so why BAUX squared is important? Well, consider now this scalar product here, which is BAU, BA squared UX. It's the same as before, but now instead of U, I have AU, and instead of AUX, I have A squared UX, okay? You do all your computations again, what you find at the end is that you recover the norm of BA squared UX. So you see where I'm going with this. You can iterate this process n time, and what you find at the end is that you recover on the left-hand side the sum of these norms here. Okay, so you have kx squared from the very first computation. Then you have BAU squared, BA squared U, and so on. Now, if the Kalman-Rank condition holds, this is actually equivalent to the normal U in L2, okay? And so it happens what happened for the 2x2 system, okay? So we recover the energy of the system that we wanted to, that we were studying, okay? So the final Lyapunov functional has a very complicated expression, okay? But once you know this, you can see that it's like an iterative expression, okay? So it's the sum for k going from 1 to n minus 1 of this scalar product here, which is BA k minus 1 times BA k, okay? And then you move to the next one, BA k minus 1, BA k, and so on, okay? And the Kalman condition ensures that at the end, this Lyapunov functional will recover the energy, as long as you find some suitable weights epsilon k, which are very easy to find in this case. So in the previous system, okay, just to show you, what happens is that the system is 2 by 2, so n is equal to 2. So, sorry, let me go here. So n minus 1 is equal to 1. So you only have one term here, which is the one for k equal to 1. So the function looks like this, like the first line, okay? But then what is BU? BU is actually U1, right? Because B is this matrix here. And BAU, if you do the computation, is actually U2. So you recover exactly the function I showed you before, okay? Except now you're doing it in an algorithmic way, okay? If you want, it's just a formula in this case, right? But it can be seen as an algorithm. You just multiply until you find the final Lyapunov function. All right, so this concludes the symmetric case. What we did in our paper, now you have the tools to at least understand our main result, which is the case of non-symmetric relaxation. So before, the matrix B was a symmetric matrix. But there is a problem here, which is that a lot of systems in physics don't have a symmetric matrix for the relaxation. They usually have a non-symmetric matrix. This is actually because when you couple two variables together, okay, so before we saw that U1 was coupled to U2 using this term here with a derivative in X. Okay, but oftentimes this does not happen. A lot of times the coupling is done by adding and subtracting the two opposite variables, okay, just without a derivative. So in this case, U2 is coupled to U3 in this way, right? So here you have minus 2U3, and here you have plus 2U2. So there is no X derivative. And this happens a lot. So you take thermoelasticity systems, Timoshenko systems, Bresse systems, a ton of hyperbolic systems in physics have this kind of property. So what do we do in this case? Well, the first step is to notice that algebra tells us that the matrix B, yes, is non-symmetric, but it can be split into a symmetric part and a skew-symmetric part. Okay, so this is what we do. We take the matrix B, we split into BS, symmetric, and BA, skew-symmetric. Okay. Well, then, this gives us the following vector equation. Okay, so you have, it's the same as before, okay, except now we have three terms. AUX was the one appearing also before. BSU plays the role of BU that we had before, okay? And now we have this extra term BAU. Now, just to give you some intuition, it's interesting that AUX, okay, is actually a skew-symmetric term. I know that A is symmetric, but the derivative in X is actually skew-symmetric because when you bring it to the other side of a scalar product, you find a minus, okay? So this is a skew-symmetric term, and this is also a skew-symmetric term. So in the end, it's like the whole sum here plays the role of AUX before, except now it's inhomogeneous. So our first result was actually the same as in Bouchard-Zouazua, where we say that if you satisfy the inhomogeneous Kalman-Rank condition that you see here, okay, which now depends on the frequency, okay, because we move to the frequency space in Fourier, so you will have a weight which depends on the frequency, which is not good, of course. But if you satisfy this Kalman-Rank inequality, then you can show that your system decays at least polynomially. And the proof is actually quite similar to the one in Bouchard and Zouazua. So you construct the Lyapunov function, like this one, which is, again, as again, the same iterative structure, okay? And you recover some norms when you get to n, and then you recover the energy. There is a problem, though, which is that I said the energy decays at least polynomially, okay, which is not a nice thing to say in mathematics. At least polynomially is not very nice. Why does this happen? Well, this happens because now the norms you recover have a weight, so they depend on the frequency in some non-trivial way. And so the only thing I was able to show is that there exists an alpha such that the norm you recover are equivalent to 1 divided by xi to the power 2 alpha norm of u squared. Now this is a limitation of mine, okay, is because I'm not as good in linear algebra. So if some of you is better at linear algebra, maybe you can quantify this alpha, but I was not able to say exactly what this alpha is. Okay, so I was only able to say there exists alpha such that this happens, okay? So this created a problem, right? Because we have a theorem, but in the end, what you're interested in is how fast the energy is going to zero, okay? Not just that it's going to zero. So what do we do? Well, here I can finally introduce the algorithm that we discussed in our paper, okay? And this is more complicated than the simple Lyapunov functional that I showed you earlier. So actually, let me go back here, okay? So what was the problem of this Lyapunov functional? Because you can say, okay, well, actually, this works every time, okay? Which is true, but this Lyapunov functional is extremely complex, if you think about it. Like, way more complex than the one in Bouchard and Zozua. Why? Well, because now you have terms with inhomogeneous, like, you have this psi here, basically. Okay, so suppose that k is equal to 3, I don't know, okay? If k is equal to 3, well, I psi a plus ba, okay, if you expand it, is 4 terms. Here, you have I psi a plus ba to the power of 2, which is 3 terms. So this is already 12 terms, okay, which is a lot, okay? And the Timoshenko system, for instance, is a system 4x4, very easy to study. And for a 4x4 system, you need this k to be equal to 3. It makes no sense to introduce a Lyapunov functional this complicated. So we went back to the idea of Bouchard and Zozua, but without looking at the full functional, but just at the single steps, let's say. So what was happening in Bouchard and Zozua was the following, that first you multiplied by u, and this gave you a certain norm. Okay, in the case before, it was the norm of u1, but this is also what happens here. Then, what do? You go to the equation of u1, and you see u1 is connected to u2 with a derivative in x. Okay, so you multiplied by, you considered this functional here. If you remember, this was the one I showed you early when I was showing you the iterative process. Okay, so this is bsu, bsau, which turns into u1, u2x, okay, which is what you want to recover the norm of u2. Now, u2 is coupled to u3, not with a derivative, okay, but without a derivative. So this means that you will have to use the other skew dissipative term, not a, but ba. So you take the previous term, bsau, which was u2, okay, and you multiply by bsa, bau. This is like playing with Legos, basically. Whenever you have a coupling with a derivative, you want to use a. Whenever you have a coupling without a derivative, you want to use ba. Okay, and you can show that this algorithm here actually will recover the norm of the energy if the inhomogeneous Kalman-Rank condition holds. But crucially in this case, the Lyapunov functional is simple enough that you can estimate the alpha, okay, giving you the decay of the solutions. Okay, so in this case, for the case of this system, for instance, you can show that you have polynomial decay in high frequencies and polynomial decay in low frequencies, and you can even estimate the alpha, which in this case is equal to -1/2. Okay, so yeah, this completes level 3. I don't have much time. There was a final case, which I wanted to show you, but now we'll just mention it, which was actually the crux, okay, of our paper, the big challenge of this algorithm. Because what happens in a lot of systems is that things, when you have both A and BA, things are not as easy as I showed you now. Okay, so it's not always that one variable is just connected to another variable, which is connected to another variable, and so on in an iterative fashion. Sometimes you have that U1 is coupled to both U2 and U3, but with 2 different mechanisms. Okay, so we needed to treat this term too. With this term here, obviously, you can treat it using the very complicated Lyapunov functional at the beginning if you just want to know that the energy goes to 0. But we want to estimate the rate, okay? And here was the very complicated part. We studied a lot on how to do this. And again, I will skip this. But the interesting part was that when we went to see how people do in the literature, okay, we noticed that most of the times they do these multiplications which are useless. They don't recover any norm, okay? The idea was that researchers noticed that sometimes if you cancel scalar products that appear in your computations, you can actually recover the norms you need, okay? Again, this is very end wavy, I understand, but there's a time constraint. So what we did in the end was to check again our computation, and we found what we called informally a magic functional, because it was crazy that this kind of functional here, this kind of scalar product, was working for canceling every scalar product that you wanted, okay? You will have to believe me here, but this completes the level also for the mixed case. And just to conclude, this is the algorithm at the end, right? So if you have a certain hyperbolic system, and you want to recover a term appearing with the derivative, then you multiply by A. If you want to recover a term appearing without the derivative, you multiply by BA. And if you want to recover both, you will need to use A, BA, and this magic scalar product that I showed you before. Now, to conclude, what we showed in our paper was the first result, the one about inhomogeneous Kalman rank condition. The second result was the general algorithm that I'm actually writing in Python. So at the end, you will be able to just plug your system in Python, and this will give you the Lyapunov functional. And finally, actually, this algorithm has even an extra, let's say, property, which is able to capture cancellations in the parameters of the systems, like it happens, for instance, in the Timoshenko system, where if the parameters are equal to some specific values, okay, then you get a better dissipation. Okay, so Timoshenko decays polynomially every time, except when the values are at certain values equal to 1, then it decays exponentially. Okay, and we're able to do this automatically using this kind of algorithm. But for this, you have to either send me an email or talk me after the talk, because certainly there is no time. And what is the next level? Well, first of all, we need to study the optimality of the algorithm, because it's not clear if we recover the optimal decay rate. And then there's several kind of extensions that we can do on the equation. One I'm particularly interested to is to consider the case where you have a parabolic dissipation, because it should be easy to include in the algorithm. It's just an extra matrix that you need to know how to merge to the others. So you will have 4 different cases probably in this case, but you should be able to still build the Lyapunov function. And yeah, with this I conclude, and thank you for your attention.
Thank you. Are there questions? Okay.
Thanks for the nice talk. In control theory, I mean, you usually have this like no autonomous equations in the finite dimensional case, right?
Yeah.
And for the autonomous one, you have the Kalman conditions. For the non-autonomous one, you also have different criteria when your coefficient depend on time. Do you think that you can use those that I don't really remember right now, but there are criteria in your particular case to consider metrics that depends on time?
Right. So the short question is I don't know, because I don't know this kind of criteria. So I should see if they can. So usually the problem is always that you want to pass from finite dimension to infinite dimension, because you have a derivative in x. Mm-hmm. Luckily, you have the Fourier transform, which tells you that as long as you have some uniformity in psi, for instance, in our inhomogeneous Kalman condition, the uniformity in psi is that this has to be solved by every psi in R. Okay, so it has to hold for every psi. Mm-hmm. So if you can move, so you can consider your system, transform everything using Fourier, then your matrices will still depend on time. Okay, and if you are lucky and you don't have problems with the frequencies, then yes, technically you should be able to apply this. But obviously, like as I said, today I've been extremely end wavy. This stuff is more technical than it seems. So I cannot say at this time, let's say. Okay, but thanks. It's a nice idea, sure.
Are there other questions? I would just ask something. In the case in which you introduce the second order derivative in the equation in space, is the inhomogeneous Kalman rank condition the same, or is it a different form?
Very nice question. So no, it will not be the same, for sure, because the thing is that you need to decide, you need to understand here what matrix is playing the role. So let's go back to the Beauchart-Zouzoua setting, okay? So this is the easiest setting possible, okay, where you have A and B, okay? So it all comes down to understanding if you want to work with the Kalman condition, okay? So our algorithm actually, so it's interesting because this this magic functional here is not something that you would see using the functional of Kalman. So it's not that we are taking functional of Kalman and canceling some terms, and then we get our function. It's something completely different. But if you want to work with the Kalman condition, you need to understand in your equation, which has now several terms, what is the term playing the role of A, and what are the terms playing the role of B. So in our setting, for instance, the role of A here in this equation, which is the simple equation, was played by AUX plus BAU. Okay. What will probably happen with the parabolic case is that the role of A is still played by AUX plus BAU, and the role of B now will be played by BSU plus CUXX, because generally, when you have a parabolic term, this introduces dissipation. So I would expect to see it in, let's say, in the dissipation term, which is given by B. Okay.
Yeah.
Now, obviously, you could say, well, if C, the matrix, is non-symmetric, then you should split the matrix too. But of course, like, you go step by step, right? So usually C is symmetric in physical systems, so I would consider that case at first. And then, yes, probably you will get a Kalman condition, which is, sorry, let me go to the inhomogeneous one. So you will get a Kalman condition, which is BS plus C xi squared, okay, which will be your fixed B matrix, times IXIA plus BA to the K, for K going from 0 to n minus 1, I think. But it's something that we have to study.
Okay, thanks. Are there other questions? Okay, we can thank Lorenzo again for the talk.